proof of claim. So assume n is a power of 2. Doesn't really matter, but this will just keep it cleaner. And this organizational tool to count up the work is called the recursion tree. Okay? And we'll see this again on Tuesday. This turns out to be a quite powerful argument, but I want to get you used to it just in the context of merge sort. So the idea is to organize all of the different recursive calls spawned by the outermost one in a tree structure. Okay? So at the top, so level 0 is the outermost call to merge sort. Okay, so this is the root of what's going to be a tree. And think of sort of each of these part of the original input array attached. Again, this is just a conceptual device. So this is just how we're going to organize things. Then we have level 1, which are the first recursive calls. All right, so this node is going to have the first half of the input array, and this node will have the second half of the input array. And then they make their own recursive calls. And so this is then further split in 2, and so on. And eventually, as we keep going down this tree and the array sizes get smaller, eventually we bottom out once every array gets down to 1. Okay? And where do the dots end? And what do these leaves mean? These leaves are the single element arrays. Okay? So quick question, what is the level number of these leaves? And so the level goes up by 1 each time I go down. What's the level number once we get to the bottom?
Log 2 of n.
Log 2 of n. Exactly, because what was log again? Log is how many times you got to divide by 2 until you get down to 1. Okay? So at the top, we have an array of length n. We're dividing by 2 every time. It takes us, by definition, log base 2 of n to get down to the single element arrays. So that's where log comes in. Okay? All right? So why is this helpful? Well, the key idea is to analyze the work done by merge sorts level by level. Okay? So it turns out if we just think about slices of this tree, that it's actually quite easy to see how much work we're doing. So what's the pattern? Okay? First level, J, right? So starting with 0, going up to log base 2 of n. So there are blank subproblems. Of size blank. What we need to fill these in is something which depends, it's a function of the level number j. So let's start with the first blank. At j, how many subproblems are there? In other words, at level j, how many nodes are there in that tree? 2 to the j. Right? So at the top level, there's 1. Okay, so at level 0, there's 2 to the 0, and then it doubles every level. So it's going to be 2 to the j. What's going to be the size, i.e. the array size attached to each subproblem at level j?
N over 2 to the j.
N over 2 to the j. Good. The array, which has length n, is distributed evenly amongst the 2 to the j subproblems at that level. So each has got to have the same number, n over 2 to the j. Is there a question over here, or that was to answer the question? All right. So I promised it was easy to figure out each level at a time, so let's do that. What is the total number of operations we have given level j? Well, let's just multiply it out. We have, okay, so a level j. We know we have 2 to the j subproblems. We know that the size of each subproblem is n over 2 to the j. Okay? And now, what is the actual work that we do? Okay, so in a call to merge sort, what do we actually do? Well, we do the recursive calls, and they do whatever they do. Outside the recursive calls, all we do is we merge. Okay? So when I speak about the work done at level j, I mean the work done at these recursive calls, not counting what's done at later recursive calls. So what I really mean is the work done by merge subroutines at these 2 to the j subproblems. And the first thing we did is we figured out how many operations merge needs. So if you pass merge an array of length m, and I guess I erased it, sorry, it was right here. If we pass merge an array of length m, here m is n over 2 to the j, then it needs at most 6m operations to do the merge. So remember, this is basically our m. And we put a 6 there. Okay, and so again, where does this come from? Number of subproblems at level j, work done per subproblem at level j, not counting what's done by the recursive calls. Okay? And what is this? This is just 6n. Okay? And what's kind of cool is that we get something that's actually independent of the level j. Okay, and the reason that happens is because it's basically a draw between the forces of good and the forces of evil. Subproblems are doubling, but sort of the work doing per subproblem is halving, so they cancel out. Those two forces cancel out. So we get in the end, we get an answer that doesn't even depend on the level j. 6n per horizontal slice of this tree. So what's the total? So the total is, well, we do at most 6n per level. How many levels are there? Log base 2 of n plus 1, because we're actually starting counting the levels at 0, and this is exactly what I promised you. Okay? So QED. All right? So that's the runtime analysis as merge sort. As I promised you, we'll do a much more general version of this recursion tree argument on Tuesday. It's something called the master method, and I'll show you some more applications, including to integer multiplication. Questions about this analysis, about this proof? Yeah?
Does it not need to add 1 to the last level?
Yeah, so it's a good question. So you can make a case for that. So I guess the way I'm thinking about it is you at least have an operation to check that you're in the base case at the end. But again, this is sort of, and this is exactly what I'm about to talk about. I mean, so you could quibble with, a +1 here, a -1 there, that kind of thing. But it's not going to matter in this course. So I agree with the spirit of your comment, though. Other questions?
How precise is the concept of fit? Because it seems like but there are a lot of operations like what basically like a bunch of different things are not really common.
Right. So I agree. It's sloppy, and these comments will largely be to explain why we're being sloppy. But I agree with the comment. Other questions? Yep.
That number 2J is the root.
That's right.